Hey, Mrs. Radigan here with a lesson on solving rational inequalities. So a rational inequality is an equality that contains at least one rational expression. Instead of its solution being a number or a couple of numbers, it's a set of numbers. So it's all the x values that make the inequality true. When we solve rational inequalities, we want to move everything to one side or get the inequality to 0. We are then going to combine all of the fractions to create one fraction on one side of the equation. We are going to factor the numerator and the denominator to find the critical values, the places where the sign changes from outputs of positive y to negative y. Those come from the x-intercepts, which are the zeros of the numerator, and the discontinuities, which are the zeros of the denominator. Then we're going to put those values on a number line, and we're going to determine where the values are positive. If our expression is greater than 0, we want those positive intervals as our solution. Or where the values are negative, if our expression is less than or equal to 0, we want those intervals. Or where it is equal to 0 and undefined. So we will identify those regions that satisfy the inequalities. Positives would be greater than 0, negatives less than 0. And we write our answer in interval notation. And there's some information on interval notation. Okay, in the first example, we said step number 1 was to get everything on one side, so we have an inequality set to 0. So we're going to move the 6 over to this side by subtracting 6 on both sides. But when we do that, we need a common denominator. So when we have a minus 6 over here, we need to come up with a common denominator. So since the first fraction has a denominator of x minus 3, we're going to multiply the negative 6 times x minus 3. Then we want to put these two fractions together. So we have 4x minus 6x. Don't forget to distribute that negative over to the negative 3. So we actually have a plus 18. That is a common denominator of x minus 3. If we put the like terms together, we get negative 2x plus 18 over x minus 3, less than or equal to 0. So this graph over here is actually a graph of negative 2x plus 18 over x minus 3. And we found the x and y intercepts and the vertical asymptotes from that. When we think about the inequality here, we want to think about where the graph is positive and negative. So this line right here is the divider between positive y's and negative y's. If we want this expression to be less than 0, we want all the values of x that make it negative. So we would want the values of x here and here, because those all lie below the x-axis or in the negative y region. Here's how we find those values, by using our critical values and our signs. So we want to know what the x-intercepts are using the algebraic function here. If the numerator has a common factor of negative 2, we can factor out a negative 2, and we have negative 2 times x minus 9 over x minus 3. We now see that we have x-intercept where there's a factor of x minus 9, so we would put a 9 as a critical value. And we have a vertical asymptote of a factor of x minus 3, so that is x equals 3. So our two critical values, the places where the signs can change from positive to negative, are 3 and 9. If we go back to the graph, we see that at 3, we have a vertical asymptote, so we actually pick up our pencil and draw the graph up here. And then at 9, we cross over the x-axis, and it can go from positive to negative. So if we look at the sign patterns of this, we're looking at the signs when we plug in a number to this equation right here, which I should have wrote is less than or equal to 0. So negative 2 is always going to be negative. If we plug in something like 0, 0 minus 9 is also a negative, and 0 minus 3 is also a negative. So we get a net negative. So this function lies below the x-axis when x values are smaller than 3, just like we see right here. If we plug in something between 3 and 9, like 6, we would get a negative for the 2. We would get a negative for 6 minus 9, and we would get a positive for 6 minus 3. So this gives us a net positive, which we see in this piece of the graph right there. Then we go bigger than 9, something like 10. Negative 2 is always a negative. 10 minus 9 becomes a positive, and 10 minus 3 becomes a positive. So one negative and two positives make a negative, and we see the graph falling below the x-axis there. So what that means is we're looking for values, outputs that are less than 0. So that means we're looking for negative values. Our negative values are values less than 3 and values bigger than 9. So our interval notation becomes negative infinity to 3 and 9 to infinity. But we need to know if we're putting parentheses or brackets on these values. So if 3 is a vertical asymptote, it's a discontinuity and can't be included. If 9 is an x-intercept, as long as the function can be equal to 0, then we would want to include that value. Okay, next inequality, we have x minus 1 over x plus 2 is less than 3. So step 1 is to move the 3 to the other side. And then we need to create a common denominator. So the denominator in the first fraction is x plus 2. So we need to multiply the top and the bottom of the term 3 by x plus 2. And that's going to give us x minus 1 minus 3x minus 6 all over x plus 2. That's less than 0. And we can put all that together by combining like terms, and we get negative 2x minus 7 over x plus 2, which is less than 0. So this function right here is graphed over on the right. Again, we're less than 0, so we're looking for negative values. So those negative values would be below the x-axis, where y is negative. So right now we can kind of see where those values are. Right here, left of negative 3.5, and right of negative 2. But let's go ahead and solve this algebraically. So this is not factorable, so we're just going to go ahead and look at our fractions. So our x-intercepts come from the numerator. So we have a factor of negative 2x minus 7, which gives us a value of negative 7/2. And then we have a vertical asymptote with our denominator factor of x plus 2, which gives us x equals negative 2. So we're going to go ahead and place those numbers on the number line here. So we have a negative 3.5, and a -2. And we're going to go ahead and test some values. So something smaller than -3.5, like -4, when we plug it into our function up here, we have -2 times -4 is +8 minus 7 is actually a positive value, and -4 plus 2 is a negative value. So a positive over a negative creates a negative. Something between -3.5 and -2, like -3. Again, when we plug it into this here, -2 times -3 is 6, minus 7 is a negative, and -3 minus 2 is a negative. So this makes a negative over negative and a positive. And when we test something bigger than 2, like 0, -2 times 0 is 0, minus 7 is a negative, and then 0 plus 2 is a positive, so this is a negative. So our solutions, since we're looking for negatives, are going to be to the left of -7.5 and to the right of -2. So -7.5 is an x-intercept, and -2 is a vertical asymptote. So when we're deciding, so we wanted negatives, -infinity up to -7. When we're deciding if we include -7/2, since this is a 0, we have to look at the inequality. Since it doesn't have an equal sign, we don't want to include it. And we never include a vertical asymptote because that's a discontinuity. So our solution is -infinity to -7/2 union -2 to infinity. Okay, and our last one, again, we're going to move everything to one side. So x over x plus 3. We add 2 to both sides and make a common denominator. So plus 3 over x plus 3. This time we're looking for greater than 0. So we're looking for positive values of x, or of y. We're going to put all that together. So we have x plus 2x plus, distribute that 2, we get 6 over x plus 3 greater than 0. So we have 3x plus 6 over x plus 3 greater than 0. This is the graph here, and we see that values of y that are greater than 0 lie left of -3 and to the right of -2. So algebraically, to find those solutions, we would factor this numerator. So we have 3 times x plus 2 and x plus 3. So our critical values lie at -2 and -3. And we're going to put those on the number line, and then we come up with our signs. So we have left of -3. So we're going to find the signs here. If we plug something in left of -3, like -4, -4 plus 2 is a negative. -4 plus 3 is a negative. So we have positive outputs in between -3 and -2, like -2.5. -2.5 plus 2 is a negative. -2.5 plus 3 is a positive, so that's a negative. And then something bigger than 2, like 0, gives us a positive over a positive, which is plus. And we want positives because this thing was greater than 0. So we would be from -infinity to -3 and -2 to infinity. And then we just have to determine, since this is a vertical asymptote, we don't include it. Since this is an x-intercept, but it's not equal to 0, only greater than 0, we also don't include that. So when you're looking for critical values, you want the x-intercepts and the discontinuities or the domain restrictions, and you need to find the signs of each. and see where your function is positive or negative.